Welcome to what is probably the most unusual lecture of this course, which I would like to begin with two quotes. One of them you've probably seen before. If your only tool is a hammer, then every problem looks like a nail. And another, which perhaps you haven't. If philosophy is outlawed, only outlaws will do philosophy. So, what is this lecture about? Well, this is a bit of a self-indulgence. So this is a selective, critical review of statistical inference as it's commonly practiced. This lecture grew out of my realization through many years of teaching statistics and also working as an econometrician, speaking with many students and speaking with many colleagues, that statistical inference is really extremely confusing. And even people who've studied it for many years are often quite uncertain about the meaning of some of the practices that we use. So if I'm doing things right, you should end up more confused at the end of this lecture than when you started out. But I hope that that confusion will be productive and push you to think more deeply about what exactly it is we're doing when we calculate a confidence interval or a standard error or carry out a statistical test. This slide is jam-packed with references, so I would strongly recommend getting hold of the slides from the course website. All of these links will take you to papers, books, and other resources. So there are further references that are also linked below. These are just a few that I think are particularly nice references. The first one, An Introduction to Probability and Inductive Logic, is a great book by Ian Hacking that can either be used as an introduction to probability for philosophy students or an introduction to philosophy for people who know probability. So if you're viewing these lecture slides from the Oxford Network and you click on this link, you'll be taken to the Bodleian website where you can view this book for free online. All right, let's start up this lecture with a warm-up exercise. This one looks simple, but it may surprise you. So imagine that two researchers carried out independent studies to answer the same research question. So they are estimating the same parameter. The first researcher reports an effect estimate and a standard error of 25 plus or minus 10. So to be clear, the effect estimate is 25, and then the standard error is 10. The second reports 10 plus or minus 10. So this is the effect estimate and a standard error of 10. So the first question I'd like you to think about is, for each of these studies, are the results statistically significant at the traditional significance thresholds? So do that for the first study and for the second. Then I would like you to consider whether there is actually a statistically significant difference between the results of the two studies. And there you'll need to use the fact that these studies are actually independent. So take a few minutes, pause the video, and then you can check your calculations against my solutions on the course website. This example illustrates a really common source of confusion that unfortunately is still easy to find in journal articles and in conversations between researchers. The punchline here is that you should not compare statistical significance. Just because one effect is not statistically significantly different from zero and another is, it doesn't mean that the two effects are statistically different from each other. So if you want to compare two effects, then you need to compute the standard error of the difference. This is an alarmingly common error, so it's really good not to fall prey to it. At the bottom of the slide, there's a link to a nice article that explains this problem in some more detail, and it also points out a number of examples where people have fallen prey to this particular fallacy in the real world. All right, so now that we've talked about statistical significance, perhaps we can talk a little bit about p-values. So here's another short exercise for you. I'd like you to consider each of these two statements and evaluate whether they are true or false. If false, I'd like you to try to explain why they're false. First, a small p-value indicates the presence of a large effect. And second, I tested the null hypothesis that my treatment has no effect against the one-sided alternative that it's effective, so that it has a positive effect. My p-value is 0.01, so that means there's a 99% chance that the treatment is effective and a 1% chance that it's either ineffective or harmful. So what do you think about these? Spend a few minutes to ponder, and then head over to the course website to check your solutions against mine. All right, with that little warm-up out of the way, let's delve into the logic of hypothesis testing. The reason why statistics is hard is because it's actually concerned with a number of seemingly different sorts of things. So one of those things is the question of belief. So if I observe some evidence that may have come from an experiment or some other data source, what should I believe after I see that evidence? Or how should I change my beliefs? Another question is, well, how should I act? What should I do in a given situation? I've seen some data. I've got to make a decision about what action to take, and how can I come up with a kind of a reasoned basis for action based on evidence? And then a third question is, well, what actually counts as evidence for some theory? Now, you may think to yourself that these are all intertwined, and they are, but they're also distinct. We could ask what evidence is, perhaps without necessarily taking a stand about belief. Maybe belief sounds subjective, maybe evidence sounds objective. That's a possible interpretation. And, evidence doesn't necessarily have to be directed towards action. So there's at least some kind of daylight between these three ideas. So I'd like to use them to frame a discussion that follows and kind of point out some differences between different approaches to statistics. So the Bayesian approach, and I will just put my cards on the table and I will say that I think that in general this approach has a lot going for it. The Bayesian approach centers on the question of rational belief, so number one. And if you combine number one with sort of models of rational choice of the kind that we would use in economics, then 2 and 3 will flow naturally from 1. So the Bayesian approach sort of integrates 1 with 2 and 3, and it does this by using what looks very much like economic reasoning. On the other hand, the frequentist approach, which is typically what you'll learn in an introductory statistics course or even in a more advanced statistics course or an econometrics course, is generally quite uncomfortable with 1. So frequentists get nervous when you use the word belief. And there are different ways of trying to talk about 2 or 3 if you're a frequentist. So if you're a frequentist, maybe you don't like 1. Well, the Neyman-Pearson approach is quite stark. It says, listen, 3 is totally impossible. It's not possible to learn about the evidence for or against a theory. Statistics is actually all about 2. Statistics is about actions. Then there are other people who say, well, I don't know, 2 is quite limiting. And it sounds like science must be about evidence in some way. So this view, the view that maybe, statistics is not just about actions, probably goes back, of course, Bayesians think that too, but among frequentists, that idea definitely is associated with Fisher, and more recently with Deborah Mayo. What's interesting to me is that the common practice, when people actually use statistics in their work, is some kind of a weird combo of Fisher and Neyman. Now, it's not weird from a mathematical perspective. All the mathematics is totally internally coherent. The problem is that the interpretations they sort of sit rather uncomfortably with one another. So Fisher, for example, held very different views than Neyman. And, this was reflected in the sort of approach that he took and the way that he explained what a p-value means or why you might use one. So there's something kind of uncomfortably schizophrenic about the way that these have all been wrapped up together in one nice, neat package, because they're not really so neat after all, as I hope to kind of convince you in the next few slides. We're going to be talking about logic today, and we will start off with maybe the simplest example. So this is deductive logic, and we're going to talk about roughly how this works. So a valid argument is any argument such that if you put true premises in, you get true conclusions out. Valid arguments are risk-free arguments. That's a quote from Ian Hacking's book. So that means there's no risk that you're going to get the wrong answer as long as you put in the right inputs. And here are 2 very common examples of deductive logic. One is modus ponens. If A, then B. A, therefore B. All ravens are black. Mordecai is a raven, therefore Mordecai is black. Modus tollens, on the other hand, is if A, then B, not B, therefore not A. All ravens are black, Django is purple, therefore Django is not a raven. Now, inductive logic, on the other hand, is about risky arguments. So here's another quote from Ian Hacking's book. Inductive logic studies risky arguments. A risky argument can be a very good one, and yet its conclusion can be false, even when all the premises are true. Most of our arguments are risky. Here's an example. When we try to generalize from a sample to a population, we might say, well, X is true in my sample. My sample is representative of the population, so X is probably true in the population. That's an example of inductive logic. All right, so let's go back to this p-value idea, and let's see if we can try to connect some of the reasoning that's involved in a hypothesis test to what we saw for deductive logic a couple slides back. So let's suppose I tested a null hypothesis, H0, and I obtained a p-value of 0.01. If the null is true, then this should only happen 1% of the time. Here's a quote from Fisher. This means that either an exceptionally rare chance has occurred, or the theory is not true. And this is called Fisher's disjunction. Now, this resembles a modus tollens. Remember the modus tollens from before, or contrapositive? But this is a risky argument. It's not a deductively valid argument, it's an inductive argument. Another thing I just should warn you about is that Fisher's disjunction, which says either this or that, implicitly assumes that all the assumptions we used to compute our p-value are correct. But of course, another possibility is that those assumptions themselves were wrong. So if maybe the data did not arise independently of one another, or perhaps one of the assumptions of the test we were using was violated in some way, then it of course could be possible that this p-value is just wrong. So it isn't really 0.01, and nothing rare happened at all. So Fisher's disjunction presupposes that all the assumptions of our statistical procedure hold. So that's the background that we assume when we explain that there's a disjunction. Okay, so here, you'll notice that Fisher was quite careful to say either something very unusual happened or the null is false. But here's how it's usually interpreted in practice. If the null is true, then this result, statistical significance, would probably not occur. This result has occurred, so H0 is probably not true. This is almost exactly like the argument with Django, but we've added probably in each case, and we now have a risky argument. Now you might look at that and say it seems quite reasonable. It sounds quite a plausible way of arguing on the basis of statistical evidence. But let me give you an argument that is logically equivalent. In other words, an argument that has exactly the same structure as the one at the top of the slide. If a person is an American, that's going to be the null hypothesis, then that person is probably not a member of Congress. Let's think about this for a second. Well, how many members of Congress are there? Well, there's a few hundred. And how many Americans are there? Well, at the time of this recording, it's about 330 million. So if a person is an American, then yeah, that person is probably not a member of Congress. Very, very, very few Americans are members of Congress. Okay, so this person is a member of Congress. Therefore, this person is probably not an American. H0 is probably not true. Notice, this has exactly the same structure as the argument from above. And the argument from above seemed really plausible. But if you stop and think about this one for a moment, it's clearly totally bogus. The Constitution requires all members of Congress to be American. If a person is a member of Congress, then this person must be an American. So in some way, this argument leaves open the possibility that we could be completely wrong. This is what it means to say that it's a risky argument. So there's something that's very tempting about this way of creating a sort of probabilistic version of this modus tollens, but actually there's something that's kind of logically deficient about it. It doesn't really make a tremendous amount of sense. And I should also just point out that Fisher was careful to say that there are these two possibilities. There's this disjunction. Well, what's going on here? It's not really that there's a disjunction, that something very rare has. I mean, I guess you could say that there's this disjunction, something really rare has happened. In other words, you've met a member of Congress. So that's kind of the resolution, is that rare things can happen. But the reason why we understand that this argument is wrong is because we've got this background knowledge that we bring to the question. And the background knowledge is that we know that every member of Congress must be American. So Fisher's disjunction does apply, but the reason that we can spot this error so quickly is because of our background knowledge. One of my favorite plays is Rosencrantz and Guildenstern Are Dead. And there's an amazing scene at the beginning of the play where the titular characters are flipping coins over and over and over and over. And the one's basically saying to the other, look, this is weird. We're getting these very strange results. Don't you think something's wrong? And there's a quote here: a spectacular vindication of the principle that each individual coin spun individually is as likely to come down heads as tails, and therefore it should cause no surprise each individual time it does. So in the play, they keep flipping the same outcome over and over and over. So heads, 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 and so on. And you might say, well, is that a very rare outcome? Well, sure it is. To get 8 heads in a row happens with probability 1 over 256 under the null hypothesis that we're flipping a fair coin and each flip is independent of the last. But, actually every sequence of heads and tails from 8 flips has exactly the same probability. So tails, 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 heads, heads, tails, heads, heads, tails, heads, tails, heads, tails, heads, tails. These all have probability 1 over 256. So maybe, and you see heads, 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 you shouldn't worry. You shouldn't think that anything weird is going on. Now, I'm not trying to trick you here. I'm trying to point out a true fact about probability. But the point that I'm trying to make is that if you were to see a sequence of all heads in a row, and you were to then conclude, that means that the coin can't be fair, what are you actually doing? Well, you're inferring from an unlikely result to the presence of a significant effect, in the words of Sprenger, and you're doing so because you presuppose that the result you've observed is much more likely under an implicitly conceived alternative than under the null. So what do I mean by that? Well, I mean when you see all these heads in a row, you say to yourself, well, that's quite unlikely if the coin is fair. But then I'll say to you, well, so are all the other sequences. Heads, tails, heads, tails, heads, tails, heads, tails, 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 heads, heads, tails, heads. Those are also extremely unlikely. So for you to say that you think heads, 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 I'm not going to keep saying it 8 times, is some evidence against the claim that the coin is fair, what you're implicitly doing is saying that you believe that there's some alternative model for what's going on under which 8 heads in a row would be really likely. So what could be such a model? Well, I guess one model might be that the coin has 2 heads on it. So if that's the case, if the coin had 2 heads on it, then both sides are heads, it's got to come up heads. So that implicit alternative would mean that, yeah, exactly, seeing these 8 heads in a row would be pretty strong evidence against the idea that the coin is fair in favor of that alternative. But you might also say, well, suppose I observe the sequence heads, tails, heads, tails, heads, tails, heads, tails. That is probability 1 over 256. And that one has an equal distribution of heads and tails. So what would make you think that one is unlikely? There's just as many heads as tails. Well, your implicit alternative here might be that somehow the sequences are being generated deterministically. Maybe someone is cheating you in some weird way, and they're just alternating heads and tails by some mechanical mechanism. And you'd say, well, that shouldn't happen if the coin was really random, because if the coin and flips are all random, then there's not going to be this very strong negative serial correlation. But again, when you do that, you're imagining an implicit alternative. Because if you thought about the situation where the coin has 2 heads, well, heads, tails, heads, tails, heads, tails, heads, tails is actually impossible. So the point I'm trying to make here is that you can't just specify a null hypothesis, reject it, and do that on the basis of the sequence of outcomes being unlikely, unless you have sort of thought about why there is some alternative that would rationalize the results you've seen and make them more likely. It's just that we don't always really think about it that way explicitly. Let's take this a little bit further. So let's go back to an example that we've already seen of Bayes' theorem. So one in 100 women has breast cancer. if you have breast cancer, we're going to call that the alternative hypothesis, then there's a 95% chance that you'll test positive. If you don't have breast cancer, we'll call that the null hypothesis, then there's a 2% chance that you will nonetheless test positive. Let's say we know nothing about Alice other than the fact that she tested positive. How likely is it that she has breast cancer? Okay, what would the p-value be in this case? Well, the p-value is the probability of the data given the null hypothesis, so assuming the null is true. So if we assume that Alice does not have breast cancer, that's the null, then what is the probability that she will test positive? That's 2%, and 2% is less than 5%, so you would reject the null at the traditional significance level of 5%. All right, but that's not the only information that we have here. We also know that 1 in 100 women has breast cancer. So if you remember our calculation from an earlier lecture, the odds of the null hypothesis given the data turn out to be 2. So the probability of the null hypothesis given the data is about 2/3. So in this case, the p-value is telling us that we've got really strong evidence against the null, and Bayes' theorem is telling us that we actually don't, that the null hypothesis is quite likely. And again, we find ourselves in this situation of getting a sort of a weird result when we try to think about a traditional significance test. And the reason is that a significance test doesn't actually answer the question that we want. We would like to know how the data makes the null more or less likely, but actually what a p-value is telling us is the opposite. It tells us how the null makes the data more or less likely. Now, rejecting the null, so having a small p-value, could be evidence that the null is false, but that will only be the case if the null hypothesis isn't too likely a priori. So if it isn't too likely before we see any data that the null is true. In this case, however, we know that breast cancer is pretty rare. So actually, this p-value does not constitute strong evidence against the null, and it's actually just completely answering the wrong question. So Bayes' theorem is answering the question you want to know, and the p-value is answering a different question that may or may not be related to the one that you really want to answer. So the point I was trying to make with the previous slide is that researchers probably want to talk about how likely the null is in the light of data. The Bayesian approach allows this, but it's really not so easy for frequentists. So null hypothesis testing, it sort of appears to relate to things about how likely nulls are, but in fact it does not. In fact, it's an error to think that just because you have a small p-value, you have strong evidence against the null. It really depends. Now, Neyman and Pearson came along and they said, look, the fundamental problem here is a simple one. Inductive logic is impossible. Don't do it. So they actually completely reject the idea of trying to get evidence about hypotheses or anything else from data. They say it's a fool's errand. It's just an impossible dream. Give up and go home. So that's a little bit depressing. But they do provide a suggestion for what we might do instead. So their suggestion is we've given up on inductive logic, so we're instead going to try to practice good inductive behavior. So we will use the data to make choices about what to do, what actions to take. So we could decide which of H0 and H1, and I want to be clear that in the Neyman-Pearson formulation, these are going to be explicitly specified hypotheses. So in the Fisher's disjunction, we didn't actually have an alternative, and I tried to make the point that implicitly we must have one if we're trying to make a claim about something unlikely occurring. But there was not actually formally an alternative hypothesis in that Fisher's disjunction. Here there is an explicit alternative. We have H0, we have H1. We're going to decide which one to accept and which one to reject. So the idea will be to design a rule, this is a decision rule, such that we will be likely to reject false hypotheses and unlikely to reject true hypotheses. So there's something a little bit weird about this, which is that we're not going to get any kind of warrant for belief or any kind of measure of evidence in a particular case when we do a particular experiment or carry out a particular study. We're just going to be given a set of rules, and if we follow them, then we know that we won't mess up too often. But we're never going to be able to tell in a given instance whether we've messed up or not. That question is off the table. It's not even a question we're allowed to ask. Okay, so there are two kinds of errors in this framework. The type 1 error is rejecting the null when it's true, and the type 2 is failing to accept a true alternative. So rejecting I should say, so the type 1 is rejecting a true null, and the type 2 is failing to reject a true alternative. Now, traditionally, what we do is we fix a type 1 error rate at alpha, and then we try to minimize the type 2 error rate subject to this constraint. So we say, look, we never want to reject a true null. So if the null is true, we never want that rejection to occur more frequently than alpha. Subject to this, let's try to make as few type 2 errors as we can. Okay, so if H0 and H1 and alpha are chosen in the light of costs and benefits, which is always a possibility, we might do that, well, then this actually amounts to what is called a very simple decision theoretic approach. So what is decision theory? Here's a quote from a famous book by Berger from the 80s. Classical statistics is directed towards the use of sample information in making inferences about theta. So say theta can be some parameter. These classical inferences are for the most part without regard to the use to which they are put. In decision theory, on the other hand, an attempt is made to combine the sample information with other relevant aspects of the problem in order to make the best decision. So the idea behind decision theory is right in the name. When we're going to be doing inferences about some parameter, we don't just think about the parameter as some kind of abstract object we want to learn about. We want to think about what knowing the value of that parameter would mean for outcomes, for costs and benefits. How would that parameter feed into decisions that we need to make? And by working backwards from the decisions we're ultimately going to make, the costs and benefits, then we can try to devise a procedure that helps us to make good decisions. And good decisions would be ones where we're weighing costs against benefits in a way that's favorable. So getting lots of benefits and few costs. Here is just one slide with a rough overview of how that looks. We need to decide which action to take in some set of actions. Unfortunately, there's some state of nature that we don't know. So that's theta. We will incur a loss of L theta A if the state of nature is theta and we choose A. And we will then observe data from a distribution that depends on theta to try to learn about what to do. So a decision rule, delta of x, is a function that tells us which action to take if we observe data x. So roughly speaking, the idea here is you're going to specify your loss function that tells what you value. That's all about costs and benefits. You know which actions are available to you. You know what information you would need to make the right decision. If you knew theta, then you could just figure out the best action, right? Because you could plug theta into your loss function, you could evaluate all the different actions, and you could choose the one that minimizes the loss. But if you don't know theta, and you only have some data from a distribution that depends on it, then the idea of the decision rule is to figure out how to map that data into the action that you're going to take. So roughly speaking, we're going to try to choose a decision rule so that we can minimize the average loss that we incurred. And notice a couple things about this. One is that you have got to specify your loss, and you could get a different answer if you choose a different loss function. The other thing to notice is that we're using this kind of long-run average idea, where we say we'd like to choose a decision rule that minimizes loss averaged over many occurrences. So we're thinking of this idea of using decision rules again and again and again and again. Sometimes we have a bad outcome, sometimes we have a good outcome, but we evaluate them not based on any individual outcome. We evaluate them on their average performance. Okay, that's all fine and well. And there are genuine decision problems out there in reality. Businesses and governments face them all the time, so do individuals. Decision theory is great. I'm a big fan. But I am not convinced that decision theory is the be-all and end-all of statistics. It's just one aspect. And Fisher was also skeptical about the idea that decision theory is everything. So Fisher wrote, "In the field of pure research, no assessment of the cost of wrong conclusions can conceivably be more than a pretense. And in any case, such an assessment would be inadmissible and irrelevant in judging the state of the scientific evidence." So, in other words, Fisher thinks that Neyman is just completely missing the point of science. So science is not about solving decision problems. Science is about learning true things about the world. Now, it may be that some parts of science do involve decision problems, and it may be that the insights that we gain from scientific research could feed into decision problems, but you can't reduce the carrying out of some experiment or some research program just to like a simple decision problem. And I think that's right. I think that we're doing more than just decision theory when we do research. So that's one problem with this Neyman-Pearson approach. A more pedestrian problem is that although the Neyman-Pearson approach sounds like decision theory, and again, I've got nothing against decision theory. It's not everything, but it can be very useful. The Neyman-Pearson approach sounds like decision theory, but actually the way it's really used in practice isn't decision theoretic at all. It's purely conventional. So we don't actually sit down and think about costs and benefits of falsely rejecting a null, versus the opposite error. We don't. We just set alpha to 0.05 for completely arbitrary reasons. There's absolutely no reason why that number was chosen. And then if you're going to try to get ethical approval for your study, you'd better have a power of 80%. Why? No particular reason. We always assume that a type 1 error is worse than a type 2 error. And all right, that might be true, but in fact, in practice, we don't sit down and think carefully about which error is worse. We're usually forced, for reasons of mathematical convenience, to set our null hypothesis to be there's no effect, or the effect is exactly equal to this particular number. So if that's the case, then it might not be true that our null hypothesis, rejecting a true null, I should say, is the worse error. So here's a null hypothesis. My null is this drug to treat terminal cancer has no effect. That's an example of a very common null hypothesis, no effect. Well, the FDA will only approve the treatment if we reject the null. And now let me ask you the question, which error is worse for a patient with terminal cancer, type 1 or type 2? I think it's pretty hard to argue that it's type 1. So this point is developed in more detail in a really interesting paper that I've linked to at the bottom of the slide that tries to understand if the FDA is too conservative or too aggressive in its rules for approving treatments. Of course, the answer may depend a lot on what the drug is. If we're considering a drug like Viagra, okay, we might not be so worried about these type 2 errors as we are in the case of a drug to treat terminal cancer. So it depends, but that's the whole point. The point is that if you're going to do decision theory, great, I applaud you, but then you've got to actually sit down and think about the costs and benefits and do it formally and correctly. This apparatus of the Neyman-Pearson approach, when it's just used in a manner that is purely conventional, doesn't do that. All right, now we've mentioned very briefly on the last slide statistical power. I'd like to end this lecture by looking at it in some more detail. So here's a little exercise to help you warm up. I would like you to write some R code to calculate a few probabilities for a normal distribution. Here, kappa and c are going to be constants. And then I would like you to think about some estimator theta hat of an unknown parameter theta. And I would like you to consider a test of the null hypothesis that theta is equal to theta naught. Suppose the null is false. So suppose the alternative does not hold. Then what is the distribution of the test statistic? As usual, you can check your results against those on the course website, and we will be using these derivations in the rest of the lecture. So please do pause, think through the answers, and then resume the video. So a quick review of some terminology. Size is the probability of rejecting the null given that it's true. It's also called a type 1 error rate. That's the term that we've been using so far. And it's also called the significance level. Power is the probability of rejecting the null given that it's false. Power is 1 minus the type 2 error rate. And economists, econometricians often talk about size and power rather than type 1 and type 2 error rates. Size is intrinsically easier to think about and to study mathematically because there's typically going to only be one way for the null to be true, but infinitely many ways for it to be false. Now, what I mean here is we are usually testing a point null hypothesis against a compound alternative. So in most applications that you'll really see out there in the wild, H naught is something like there's no effect, so theta is 0, and h1 might be theta is positive. Okay, so that includes an infinite number of possible values for theta. Or it might be that theta is not 0. Again, that includes an infinite number of possible values for theta. So there's only one way for the null to hold, but there's infinitely many ways for it to not hold when you're testing a point null against a compound alternative. So if we want to talk about power, we need to talk about power against a particular alternative. We need to pick some specific value of the parameter that isn't the null value, and then we can compute power. So given alpha and given some decision rule, so decision rule tells us when we're going to reject the null, if the true parameter value is theta, where theta is some value that is not equal to theta naught, then what is the probability of rejecting? Okay, and so here is the power calculation. On this slide, I have 2 links. If you click those links, you'll be taken to an interactive web app, well, really to 2 different interactive web apps, that will show you visually where this power calculation comes from. I think it's really helpful to look at it both as a kind of a simple calculation with normal distributions, and also as a kind of a graphical illustration of shifting around distributions and seeing how the areas under curves change. So I would really encourage you to spend a few minutes to grab the lecture slides, click these links, and play with the apps. But I will just talk you through the logic here. So for theta hat, as a test, I should say as a statistic that has a distribution normal theta with some standard error, then we can form the test statistic theta hat minus theta naught divided by that standard error. I'm going to define kappa to be the difference between theta and theta naught divided by the standard error. So what I'm saying there is how far away is the null from the alternative. So the null theta naught, and the alternative that I have in mind here is theta. How far is it measured in standard deviations? So that's what kappa is. And then I will have C. So C is going to be a critical value. So CP is Q norm of 1 minus P. Okay, so for a one-sided test of the null that theta is theta naught versus the alternative, sorry, that's a typo. It should be versus H1. It actually says versus H0. So versus H1 that theta is greater than theta naught, well, we can do the calculation. So using the results that you derived a couple of slides back, and if you need to see the derivations, please do check the exercises. We figure out that the power is 1 minus P norm of the critical value minus kappa. For a two-sided test, it's a little bit more of a pain. And the reason is with a two-sided test, there's actually this awkward fact that you can reject the null hypothesis either because you are on the sort of, you're on the right side, you're rejecting in the direction that the alternative actually lives. So let's suppose that theta was bigger than theta naught. You might reject because your test statistic was positive and bigger than the critical value. That would be kind of good, right? But you might also just get extremely unlucky, and you might reject because, in fact, your test statistic has the wrong sign. That's not terribly likely if your test actually has some power, but it could happen. And that means that there are going to be 2 terms in the power for the two-sided test to reflect each of those 2 sides where you could be rejecting. Now, one of them, in a certain sense, is wrong because it leads to you, rejecting the null of 0 because you got a test statistic that's negative when, in fact, the alternative is positive. But it is still a rejection, and so formally the way we've defined power here, that is still going to be included in the probability calculation. If you want to see what I mean in some more detail, again, I would encourage you to click on the two-sided test, play around with the web app, and you will see what I mean. This is also going to make an appearance shortly. All right, so here is another exercise for you, just to help you kind of cement what we've seen with power. You might wonder, why am I asking you to compute power? Well, this is something that you're commonly going to have to do if you ever carry out an experiment or you ever design a study that involves sampling in any way. Usually for ethical approval, they will ask you to compute the power of a test under some assumptions. So in this particular example, I'm going to have IID draws from a normal distribution with mean mu and variance sigma squared. We're going to try to estimate mu using the sample mean x bar. So I would like you to work out what the standard error is. I would like you to work out what kappa is using the notation from the previous slide. And then I would like you to plot some power curves for a one-sided test under some different choices of parameters here. So traditionally, the way that you do a power calculation is you choose a null, you've got an alternative hypothesis, and you have alpha. So alpha is your significance level, the null is mu naught, and then you have some alternative value. So suppose that the true mean is really mu, population variance, say, is sigma squared. You're also going to need that. You ask yourself, how large a sample size would I need to get power equal to 80%? So traditionally, a power calculation is about figuring out the sample size that would give a certain target power. But there's an alternative way to do the same thing. So you're still computing power, and this is called a minimum detectable effect. So in this version, you don't figure out the required sample size. You instead figure out, for a fixed sample size, n, what is the smallest value of the alternative, mu, such that I would hit a power of 80%. And if you click on the link on the slide, you can see a paper about minimum detectable effects. So to think about the difference between these, in the one, you say, my budget allows me to gather so many observations. What's the smallest effect that I have some power of finding, some reasonable amount of power of detecting? The other version says, well, if I'm trying to figure out how much data to give, and I have an idea of how large the alternative might be, how far it might be from the null, then I can hit a target power, and by asking myself what sample size I would need to reach that power. So fortunately for you, the R function power.t-test can actually do both for the two-sample t-test. So it's a very convenient function to use in practice, although it's always nice to roll your own at least once or twice in your life to make sure you actually understand what's happening. All right. I mean, power calculations are a reasonable thing to do if you're going to be carrying out frequentist inference. You really do want to make sure that you have power, and we'll see why at the end of this lecture. But there's some strange stuff lurking in the background here when we start to think about social science applications of hypothesis testing. Do you think that the effect of some intervention in social science is exactly zero? Think of any intervention you want. Do you think that that intervention has absolutely no effect whatsoever? Do you think that its effect is exactly 0.0000000 forever? Do you think that it's impossible that the effect could actually be 0.00001? Are you absolutely sure that there is no effect whatsoever? Well, that's totally implausible. I put it to you that everything has some effect in social science. It's just that some things have tiny effects, other things have medium effects, and other things have big effects. So let's go back to the previous example. Let's think of mu naught is 0. And in this case, kappa would become square root of n mu over sigma. So let's consider an alternative hypothesis. So my alternative is going to be that mu is not 0, but it's just super, super small. So maybe mu is 1 over 1,000. All right, that's fine. Even if mu is 1 over 1,000, so this particular intervention has very, very small effect, power will approach 1 as sample size grows. So think about that for a moment. No matter how small the effect, if it's not exactly 0, then as the sample size grows, you will definitely reject the null. Now, you might say, great, I want to reject the null. The null's false. But in that case, what we're saying is we've just done a test of how big our sample is. Because it's only if the null was actually plausible, it's only if the null was actually something that could have been true, that we wouldn't automatically reject it just by getting more data. This is particularly a problem, I think, in some large online experiments where you might have thousands, tens of thousands, hundreds of thousands, or millions of individuals. You will be able to detect really tiny effects. You will, in large enough samples, certainly be able to reject the null, but then so what? I mean, we kind of knew the null couldn't have been strictly true to begin with in almost all social science applications. So, to my mind, this is one of the best indictments of significance testing. There's a lot of things wrong with it, but this is a particularly stark one. My advice is to prefer confidence intervals to tests, and that you always need to think about magnitudes. You always need to think about how large is this effect relative to something that I care about and relative to something that I can quantify. Is this an effect that makes people live for 1 day longer? That's not such a big effect. Is this an effect that increases children's reading scores by 2 standard deviations? That's a huge effect. You can't evaluate the importance of an effect by looking at a small p-value. You can't evaluate the magnitude of an effect by looking at whether you rejected the null. So this is just to raise the point that economic or practical significance is actually a lot more important than statistical significance. We want to quantify uncertainty, but there's just something that's fundamentally totally sterile about the hypothesis testing exercise. It just doesn't really answer the questions that we want to answer. And it may nevertheless give us something meaningful that we can talk about. So you might be tempted to say, well, if this is all we can get, then we'll just have to settle for it. But in that case, I would encourage you to consider that there are really alternatives out there. You can consider Bayesian inference, or if you don't want to do that, you can just say, no, I want to report confidence intervals. Confidence intervals are great. They tell you the likely, or they tell you the range of values for some parameter that are not in conflict with the data, according to a particular definition of what it means to not be in conflict with the data. So now that I have poisoned the well, I suppose, in some case, when it comes to thinking about significance testing, I'd like to go back to thinking about power, because power is a very subtle but important concept. And in the final part of this lecture, I'm going to be drawing on 2 papers from Andrew Gelman and co-authors. And this example is sometimes called Of Beauty, Sex, and Power. That's the name of one of those 2 papers. And it's about a paper by Kanazawa from 2007 that found that beautiful people have more daughters. So this study looked at observational data from the National Longitudinal Study of Adolescent Health. The sample size was nearly 3,000 individuals who had at least 1 child. So each of the individuals had at least 1 child. You observe the attractiveness rating on a scale of 1 to 5, and you observe the sex of the firstborn child. So among the people in this sample with the highest attractiveness, so among the people who are rated 5, those people had 56% girls as their firstborn. And among everybody else, attractiveness ratings 1 to 4, they had 48% girls. Now you may be thinking, well, why are they comparing 1 to 4? 1 to 4 against 5? Why not 1 to 2 against 3 to 5? Or why not 1 to 3 against 4 to 5? There are many possible comparisons they might have made. And, you're right to be worried about that. I am going to sort of elide that for the moment. I will put that to one side. So let's just think about this particular comparison, and let's think about the particular test that this paper carried out. So, needless to say, this difference turned out to be statistically significant, and there was a paper published, and it received a lot of media coverage. That's all fine, except that we know that the effect size in that study is so much larger than anything that could possibly be plausible that we really, really ought to doubt it. So here's a quote from one of the Gelman and co-authors' papers. There is a large literature on variation in the sex ratio of human births, and the effects that have been found have been on the order of 1 percentage point. For example, the probability of a girl birth shifting from 48.5% to 49.5%. Variation attributable to factors such as race, parental age, birth order, maternal weight, partnership status, and season of birth are estimated at less than 0.3 percentage points to about 2 percentage points, with larger changes, as high as 3 percentage points, arising under economic conditions of poverty and famine. So in short, human sex ratios do skew under certain circumstances. But even in situations of extreme poverty and famine, you're looking at maybe 2-3 percentage points max. And let's go back to this Kanazawa paper. What do we see here? 6 percentage points. That's really, really, really large. All right, so what's going on here? Well, there's a few things that could be going on. So one possibility is the file drawer bias. So this is the idea that researchers are less likely to report findings that are not statistically significant. So the idea is that they do a study, they don't reject the null, they become discouraged, and they just leave that study in their file drawer. A related but distinct idea is what's called publication bias. The idea here is that journals are less likely to publish papers with statistically insignificant results. And I hate to tell you, but both of these two effects are pretty significant themselves. They are very common, and they probably do greatly distort which studies even make it into journals in the first place. In fact, they can give rise to an alarming situation in which most published findings in a given area could turn out to be false. So there is a great link for you here. You can click on the slide to see how that could happen. And I would strongly encourage reading it and thinking more carefully about these problems of publication bias and file drawer bias. But there's an even more nuanced way of looking at this. So even if we take this Kanazawa example at face value and we don't worry about the file drawer bias and publication bias, that mean that the fact that we observed this study means that it's not really just a representative draw from all studies that have been carried out. It's sort of an unusual draw. That's why we've been shown it. Let's ignore that. So the key problem is that Kanazawa has no power. So if you recall a couple slides back, we talked about how you can skew the sex ratio. There are various ways that can happen. In situations of extreme famine, you might go as high as 2 or 3%. But an effect of 0.5 percentage point would be pretty large based on the literature. In particular, if you're thinking about the effect of being beautiful on sex ratio, the effect of something like we talked before about age, sex, and so on sex ratio, yeah, there can be effects, but they're not large. So let's take a ballpark based on that kind of prior knowledge let's go for a symmetric deviation from 0.5, so perfectly even birth rates. That's a slight simplification. It's not actually true that male and female births are exactly as likely as each other, but just to keep things simple in this example. So what we can do now is we can consider the power of a two-sided test. I'm going to use the function power.propTest. And the sample size of each group, I'm going to give each group half of the sample, so 1,486 observations. Again, that's not exactly the case in the study. This is just a simplification. And I'm now going to suppose that the two groups have rates of 0.4975 and 0.5025. So what is the power of a two-sided test with significance level 0.05? It's about 6%. So Kanazawa's sample size and this plausible sized deviation, this deviation that could actually be biologically plausible, would give you a power of around 0.06. In other words, this study has no power. Remember, alpha is 0.05. So what this 0.06 is saying, a deviation of this size, if it were truly present in the data, would be rejected only 0.06, only 6% of the time. We're very, 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 very unlikely to reject. Well, that's weird, because, of course, Kanazawa did reject. So what's going on here? Well, to understand, we have to talk about two new types of errors that you haven't probably met before. I showed you type 1 and type 2 errors, which should be familiar from your introductory statistics course. Now I'm going to introduce type M and type S errors. So these have to do with a situation in which you have low power, but you reject the null. You can read some more about them in this Gelman and Carlin paper linked at the bottom of the slide. A type M error stands for a magnitude error. So if your test has low power and you reject the null, then the magnitude of your estimated effect is going to be greatly exaggerated. and I'll show you why in a moment. A type S error, on the other hand, refers to the fact that if your test has low power and yet somehow you reject the null, then there is a really good chance that the sign of the estimated effect is wrong. So this is very worrying. What this says is that the reason we should like people to do a power calculation and find that they have a lot of power is precisely because if they run around testing things in an environment where they don't have much power, but they reject. Now you might wonder, well, why would they reject? Now let's go back to that publication bias and file drawer bias problem. Imagine that we're only going to get to see the studies where they rejected. That could be a reason why we end up actually seeing papers that have mostly rejected the null. So if they're actually in a low power environment, if those tests didn't have much power, then we're very likely to be totally and systematically misled by the results of the test. In that, well, the test rejected, fine, but the only way it could have rejected is because the magnitude of the estimated effect is so large as to be implausible. And in fact, there's a reasonable chance that the sign is wrong. So let me show you why, and we'll end with this figure, which I took from Andrew Gelman, who says, this is what power equals 0.06 looks like. Get used to it. So what we've got here is we've got a normal distribution that is centered slightly away from 0. So there is an effect here. There is a small effect, and there is an effect such that the power of the test is 0.06. So in other words, when you shift that normal distribution, you see the blue line is not equal to 0, you shift it away from 0, then what you're going to do is you're going to shift a certain amount of probability into the upper tail and out of the lower tail. So if that blue line perfectly aligned with the red line, we would be in a situation where the null hypothesis was true. And in that case, the right and left tails would be perfectly symmetric. The red shaded region on the right and the red shaded region on the left would be exactly the same size and shape, and together they would constitute 5% of the probability. But we've actually shifted that distribution slightly to the right, so there's a little bit more area in the rightmost red shaded region than in the leftmost red shaded region. And these regions correspond to the rejection region. So they're the regions where you would reject the null hypothesis. And here the picture gives this in terms of estimated effect size. So you'd be rejecting when your estimated effect size is around 16 or greater in absolute value. Okay, so now let's take a look at the rejection region. So let's take a look at what estimated effect sizes fall into the region where we would reject, under this assumption that the true effect size isn't so big after all. So that's this blue line being only slightly to the right of 0. Well, the first thing that you can notice is almost half, not quite, let's say quite a lot of the probability in the rejection region is in the wrong direction from the null. So remember, the true effect here, that blue line, is positive. But actually, 24% of the probability in the rejection region is on the left. So that means that there's a 24% chance if we reject, so in other words, if we get a draw from the red rejection region, conditional on that event occurring, there's a 24% chance that we've actually observed an estimated effect with the wrong sign, the opposite of the true one. Even more worrying, if we take a look, now we can take a look at the right-hand tail, and that's the situation in which we reject in the correct direction. So that's a situation where our estimated effect size is positive, and indeed the true effect is also positive. Well, the only way that we can reject is if we're really quite far out into the tail. And that's because we're in a situation where there's low power. If we had high power, then this normal distribution would be shifted really, really, really far to the right, and there would be a tremendous amount of area in that red shaded region because the cutoffs along the axis would stay in the same place. They'd be about minus 16 and 16, but that normal distribution would shift really, really far to the right so that almost all of the area under that normal distribution is to the right of the cutoff. But that's not what we have. What we actually have here is just a relatively small amount of probability to the right of that cutoff. And the only effects that are to the right of the cutoff are really big estimated effects. They're quite sizable. But in fact, the true effect is tiny. So in this environment, in an environment where power is really low. If we somehow end up rejecting, then our estimated effect size is going to have to be dramatically larger than the true effect size. And there's also a really good chance that we got the sign wrong. So if you're ever wondering why people should worry so much about power, this is why. When you combine this with the statistical significance filter that leads us to journals, I should say, when you combine this with the file drawer effect and publication bias that leads us to journals typically only publishing studies in which the null hypothesis was rejected, this is a really dangerous situation to be in. So what lesson do I want you to sort of take away from this lecture? The way that statistics is practiced, or the way that frequentist statistics is practiced, really leads to some pretty perverse consequences and a lot of misconceptions. People view statistics and tools like hypothesis testing and p-values as really essential components of science, but they don't spend a lot of time stopping to think about whether the tools deliver what they seem to, or whether the way that they're used actually makes any sense. I'm not saying to give up on statistical inference, far from it, but what I'm saying is that it's really valuable to spend some time reflecting carefully and maybe even thinking a little bit about philosophy, thinking a little bit about how this whole enterprise that we called science is supposed to work. What are we trying to do? And maybe what sorts of tools would we want to develop and use to answer the questions that we care about, rather than just following a recipe that someone invented 100 years ago and everyone else just kind of copied over and over again. So as I said before, I hope that you ended this lecture more confused than when you started. If you did, I feel like I've done my job, and I would invite you to go back and click on some of the links that I provided in the slides and read through some of these resources, which will really help you to go a bit deeper into thinking about how inference works.